In this video, we're going to talk about 7.4, arc length and surfaces of revolution. So our objectives here are to find the arc length of a smooth curve. We won't really, I don't think, define what smooth is right now. We'll get into that later, but we'll just kind of define it in a simple way right now and find the area of surfaces of revolution. So we talked a little bit about surface area in one of the last videos, and I used this letter like this to stand for it. We're going to do the same thing here and use some integration techniques to help take care of that. Probably lots of completing the square in this video, so I've gone over that in a recent video, and we'll get some opportunity to practice that. So definitions before we get started: arc length is going to be the length of an arc. So then the next question is, well, what's an arc? An arc is a segment of a smooth curve. So I'll show you on a picture here what a arc is. And then if we use the word in a definition, a rectifiable curve, that's a smooth curve that has a finite arc length. So let's consider the following graph of a smooth curve. It's smooth because it has no cusps, no sharp points. So, and we don't have holes or jumps, or it's a continuous curve here. And it has no places where the derivative is going to be where it comes to a sharp point, where the limit of the derivative from the left and the right is different. So everywhere the function is continuous because the function value equals the limit from the left and the right, but the if I have the derivative function, that's also continuous. All right, so this this function is also continuously differentiable on a to b. That's basically what the general idea of a smooth curve is. We'll get into a more precise definition of the word smooth in chapter 10 when we get into parametric and polar, but it'll be a parametric definition. All right, so we have this piece of the graph right here. If I trace the graph right there, that's going to be a curve or a portion of the smooth curve that's an arc, and I can find the arc length, the length of that arc right there. That's going to be something that we're going to try to do. I can make a can estimate it by finding the length of this line and then the length of this line and move points closer and closer and so on. I can do that. That's essentially what we're doing to find the arc length, is getting the limit there, which is going to turn into a Riemann sum, which is going to turn into a definite integral, and I'll show you that in just a second. So we can partition the curve into n equals subintervals, which you see in pink there, with x0 being less than x1, being less than x2, being less than ... being less than xn, being less than, and xn is going to be equal to b. So a is going to be x naught, xn is going to be equal to b. We can apply our concept of the Riemann sum, but instead of calculating the area of the rectangle, we measure the length of the line segments created by f of x on, and then x sub k1 to x sub k. And we're going to be using this distance formula here, that if we have a triangle here Pythagorean theorem that if this is delta x and this is delta y, and we call this side d, that d squared is delta x squared plus delta y squared. So d is going to be the square root of delta x squared plus delta y squared. I'm going to make sure to put parentheses around that so you're sure that it's the delta x that you're squaring and not that you're finding the delta in x squared. So that's going to be the distance between 2 points in space. That if I have another way to write this, is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. So because of that, then we're going to have the distance is going to be approximately equal to, we know how to approximate delta y from linearization. And we're going to say, well, that's definitely delta x squared there plus, and then we can replace delta y with a delta x times f prime of x squared. Then we square that, and delta x can factor, delta x squared can factor out, and the square root of delta x squared is delta x, and left on the inside is 1 plus f prime of x sub k squared. And that's what our formula is going to look like here in just a second. This is our length of the curve as k goes from 1 to n when we had n subintervals here. As we take the limit as delta x goes to infinity, goes to 0, which is the same thing as n going to infinity. Limit as n goes to infinity here. Let's delta x go to 0 is going to be the definite integral from a to b of this function right here, 1 plus f prime of x squared. And then the delta x changes to a dx over here. And that's our arc length formula. Not super important for you to be able to prove that right now, but you just may be interested, where did that formula come from? There it is. It came from the Pythagorean theorem and from us doing linearization with delta y, and then the delta x that factored out became the dx that's out here, and that's why there's an f prime on the inside of the formula there for arc length. So let's go ahead and look at the definition here for arc length. Let the function y equals f of x represent a smooth curve. It's important that this is a smooth curve. We're going to see the word smooth in a lot of our definitions. Going forward, you're not going to be able to use these definitions if there's cusps and jumps and holes and things like that on the interval of a to b. The arc length of f between a and b is, and make sure your s has these little things on the end of it. Otherwise, it means something else in physics. It's related though. So actually, we're not there yet. It is lowercase s. So lowercase s, not capital S, because this is position or distance. It's just a lowercase s like that. Is going to be a to b of the square root of 1 plus the first derivative of f squared dx. So if instead we have a function of y, that's okay as well. We just switch from a to b. We say c to d if we're on y. Values here, dy and 1 plus g prime of y squared. That's okay too. We can find the length of the arc either way as a function of x or a function of y. The length of a segment, so let's find the arc length from x1, y1 to x2, y2 on the graph of y equals mx plus b. So those are the given points. We know that f prime of x is going to be equal to m here. So s, our arc length, is going to be a to b of the square root of 1 plus m squared dx. So in general, m is equal to y2 minus y1 over x2 minus x1, which is going to be delta y over delta x. So S is going to be a to b, 1 plus y2 minus y1 over x2 minus x1 squared dx. Just note that if we wanted to make a common denominator here, that we would have to say 1 plus y2 minus y1 squared over x2 minus x1 squared is equal to x2 minus x1 squared over x2 minus x1 squared plus y2 minus y1 squared over x2 minus x1 squared. It's going to be x2 minus x1 squared. It's y2 minus y1 squared over x2 minus x1 squared. Let's come back and plug that in. That our S is going to go from x1 to x2, square root of x2 minus x1 squared plus y2 minus y1 squared over x2 minus x1 squared dx. So we're going to get something here that we're going to integrate that is going to look like this. So we don't know exactly what this is right here, but there's going to be an x out here. It's going to be a part of it. And this is going to be going from x1 to x2, which means whatever this thing is here will be multiplied times x2 minus x1. So we have I'll just tell you what this thing is. This is there's no reason to not say this. This is square root of x2 minus x1 squared, y2 minus y1 squared over, it's all this, right? So this is going to be the square root. And when we take the square root of the top and the bottom, now S is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. And the square root of that squared in the bottom is going to give me x2 minus x1, which is going to cancel with the x2 minus x1 that's sitting right here. And we get the distance formula for the line, that this is delta x squared plus delta y squared. And that's exactly what we should have gotten for the distance between 2 points on a line. And we did it with integration, and we found out where that came from. So wasn't that fun and exciting? let's go ahead and find the arc length. Now, first example, so find the arc length of the graph, y equals x cubed over 6 plus 1 over 2x. So I'm going to rewrite that as y equals 1/6 x cubed plus 1/2 x to the negative first, because I want to find y prime is going to be 1/2 x to the second minus 1/2 x to the negative second. That's going to be important in just a minute. So we're going to say s is going to be equal to integral from 1/2 to 2 of the square root of 1 plus, and I need 1/2 x squared minus 1/2 x to the negative second squared dx. So there will be some work to do here in just a second. 1/2 to 2 of 1, and then we have plus. So when I square 1/2 x squared, I get 1/4 x to the fourth. When I multiply 1/2 x squared times negative 1/2 x squared, I get minus 1/4. When I multiply negative 1/2 x to the negative second times 1/2 x squared, I get another minus 1/4, and then I get plus 1/4 x to the negative fourth. When I go ahead and square that last term, and this is dx. So s is 1/2 and 2. And so when I add together here, negative 1/4 minus 1/4, I get a negative 1/2. Negative 1/2 plus 1 is going to be a positive 1/2. That's going to be really important that this addition of 1 changes the sign here in the middle. So we now get 1/4 x to the fourth plus 1/2 plus 1/4 x to the negative fourth dx. So I'm now going to factor that. It is a perfect square trinomial. So adding that 1 completed the square. And this is now 1/2 x squared plus 1/2 x to the negative second. Check that out if you would like to, but that's going to be 1/4 plus 1/4 now is going to give me 1/2 as my middle term. The other things stayed the same. And so this is going to be squared like that. So the square root and the squared will make each other go away. 1/2 to 2. And then this is 1/2 x squared plus 1/2 x to the negative second dx. And so we can pull that 1/2 out. Have 1/2 to 2 of x squared dx plus 1/2 to 2 of x to the negative second dx, 1/2 of x cubed over 3 from 1/2 to 2 plus 1/2 of x to the negative first over negative 1 from 1/2 to 2 is going to give me, so that's 1/6 of 8 minus 1/8, and then minus 1/2 of reciprocal of 2 is 1/2. Reciprocal of 1/2 is 2. So that is 7 times 8, 56 over 8. So this is 7 7/8 is what I'll say this is right now. 7 7/8. And then we have negative 3/2, so plus 3/4. When I do that, so this is times 2 over 2. is 7 7/8 plus 6/8 is going to be 13/8 here. Is going to be 8 5/8, 64, 60. Let's see. What am I getting different here? Just going to check this for a second. Be right back. All right, I forgot with this 7 7/8, I forgot to multiply it by 1/6 at first. So that's 21/16 for this part. And then I'm going to have, let's say I had there 3/2, 3/4, yeah, plus 3/4. So 3/4 is going to be 20. It's going to be 21 plus 12 over 16 is 33/16, which is correct. I've checked it with my calculator. So 33/16 is about 2. Let's see what that is. 33/16. 2. That's exactly 2.0625. Is what it's exactly equal to. All right. Example number 2 of finding arc length. So find the arc length of the graph of ln of cosine of x from x equals 0 to x equals pi/4. This one's going to be a bit nastier. 0 to pi/4. Square root of 1 plus, and then the derivative of this is going to be 1 over cosine times the derivative of inside is going to be a negative sign. So y prime is going to be a negative tangent of x. So when I square that, that's going to be tangent squared of x dx. So we're going to use a trig identity here. 1 plus tangent squared is secant squared. So secant x dx, and the integral of secant is ln of the absolute value of secant x plus tangent x. That's going to be evaluated from 0 to pi/4. Secant of pi/4 is going to be root 2. Tangent of pi/4 is 1. Secant of 0 is 1. Plus tangent of 0 is 0. Minus ln of 1. It's positive. I don't need the absolute value bars anymore. Ln of 1 is 0. So that's going to be S is about, if you would stick this in your calculator, 0.88. Let's take this idea of arc length now and apply it to what we learned previously about solids of revolution. And let's think about if we would revolve this curve around a line, we would get the outer boundary of a solid of revolution, we would get its surface area. And this is where I want to use that fancy looking S that I was telling you about here. So we need to think of the fact that we're doing circumference here, really, of all these little circles. So C is equal to 2 pi r. So that's what this star thing is about here. And r is this part here. So we're going to have a formula that looks like this. S is equal to A to B of 2 pi r of x here times 1 plus f prime of x squared dx. So, and this r of x is usually just going to be x or y. Just like it was with the shell method, this is related to the shell method. So the area of a surface of revolution, let y equal f of x, have a continuous derivative on the interval from a to b. The area S, the surface area of the surface of revolution formed by revolving the graph F about its horizontal or vertical axis is S equals 2 pi integral a to b of, and then all the things with the x's need to stay on the inside. So really this r of x is trapped in there, but the 2 pi comes outside like we just saw in the formula. So r of x square root of 1 plus f prime of x squared dx, where r of x is the distance between the graph f and the axis of revolution. That should sound a whole lot like your p of x or p of y in the shell method, because it is. And that's why I told you that that was really not a p, it was a rho in Greek. And now you see how it's related to the letter r for radius here. It's the same thing. So if you want to call that p there to be consistent with your shell method, I won't have a problem with that. But do whatever your teacher tells you to do in the notes, and your teacher might use a p there just because it's just like what was there in the shell method. So we have r of y is the distance between the graph and the axis of revolution here. If we write this in terms of y's instead, 2 pi from c to d, r of y, square root of 1 plus g prime of y squared dy. We can change this all up in terms of a x equals g of y there. It's the same formula. So let's go ahead and let's look at this example here, the area of the surface of revolution that's found in the area surface of revolution by revolving the graph of f of x equals x cubed on the interval from 0 to 1 about the x-axis. So we're going to get big circle here. Do my best to draw this. Then we're going to get some smaller circles here and some smaller circles still, all the way out to where we have this is like this, and we're going between these like so. going to look kind of like a trumpet or a funnel or something like that. It's just not going to go straight line there. There's going to be this curvature from x cubed there. And we've revolved about this line right here. So s is going to be 2 pi from a to b, so 0 to 1 of, and then our distance to our axis of revolution here from the axis to the function is our y, which is x cubed. And then we have 1 plus, and then if y equals x cubed, y prime is equal to 3x squared. We're going to square that, so that's going to be 9x to the 4th dx. So if our u is the inner function here, 1 plus 9x to the 4th, our du is going to be 36x to the 3rd dx. We make a nice substitution here, 36 over 36 like that to make our u substitution, and s is going to be pi over 18, and then we have a integral of u to the 1/2 du. Now I'm going to change my limits of integration to u. So 1 plus 0 is 1, and 1 plus 9 is going to be 10. So this is going to be s is pi over 18. This is going to be u to the 3/2 times 2/3 from 1 to 10. S is going to be pi over 27 times, and then this is going to be 10 to the 3/2 minus 1 to the 3/2. And so S is exactly equal to pi over 27 times the square root of 1000 minus the square root of 1. S is pi over 27. This is going to be 10 root 10 minus 1 is exactly what the answer is. So if we need an approximation of that answer, it's approximately 3.563. All right, that's it for this video, and we're going to come back next time and talk more about work, center of mass, and these other applications of integration next time. See you for the next video.